Hello everyone and welcome to another video with Liah. Today I'm going to be doing part 1 of a chemistry exam review. The review is going to be in the format of practice questions, which I will be solving throughout this video. The questions are going to address topics such as percent composition, classification of matter, conversions between moles, grams, atoms, and molecules, density, dimensional analysis, and naming compounds. I really hope you enjoy this video. I encourage you to get out a pencil and paper and a calculator and a periodic table to follow along as I do these questions. What is the density for a liquid with volume 12.35 milliliters and a mass of 5 grams? Well, you should recall that density is mass over volume, and so we have that the density is equal to the mass of 5 grams over the volume of 12.35 milliliters. Okay, so you divide 5 by 12.35. And this will give you the answer of 0.40 for the density. A homogeneous mixture has a something composition, while a heterogeneous mixture has a blank composition. Alright, so we know that homogeneous, is going to be a uniform composition, and a heterogeneous mixture is going to have a non-uniform composition. Okay, remember that homogeneous mixture can be like air, right? So you don't really see the differences. Okay, everything has a uniform composition. While an example of a heterogeneous mixture is like soup with chunks of carrot, right? And there you can see differences in the mixture. What is the volume of a block of zinc that has a density of 7.13 grams per centimeter and a mass of 2.41 kilograms? So we know that density is mass over volume, and if we go with our shortcut with this circle with mass over density and volume, we know that the volume is equal to the mass over the density. Okay, so volume is mass over density, which means that in this case we have volume and we have that equal to a mass of 2.41 kilograms over 7.13 grams per centimeter cubed. However, notice that we have kilograms and grams involved. So that means we either need to convert this amount of kilograms to grams, or convert this amount of grams to kilograms. So what I'm going to do is I'm going to convert 2.41 kilograms to grams first. And here we know that 1 kilogram is equal to 1,000 grams. Alright, so to cancel out kilograms, I'm going to multiply it by a kilogram at the bottom and 1,000 grams on the top. So we have kilograms on the top and bottom, so kilograms cancel out and we are left with grams. This is going to give 2,410 grams. So our equation here is volume equals 2,410 grams over 7.13 grams per centimeter. And this gives 338.01 centimeters cubed. And also note that volume, can be centimeters cubed or counted in milliliters. And we have this, And we know that this is true, that 1 centimeter cubed is equal to 1 milliliter. There are 5.6 times 10 to the 6th nanograms Ng of a powder. What is this mass in grams? We know that we are going to start with nanograms and we're going to convert this to grams. So with this we know that in 1 gram there are 10 to the 9 nanograms. And we start off with our equation, so 5.6 times 10 to the 6 nanograms. So I'm just going to put it over 1 so we can see the fraction. And then we're going to multiply this by the conversion factor in such a way that the nanograms cancel out. And we know that in order to cancel them out, we have to put nanograms at the bottom. So 10 to the 9 nanograms, and we have 1 gram on top. Now that we have nanograms on the top and on the bottom, we can cancel out that unit, leaving us with the unit that we want. And so when we multiply straight across, make sure to put this in parentheses, okay, so that it is properly divided by 10 to the 9. The answer here is 0.0056 grams. A rocket is traveling at 549.99 miles per hour. What is its speed in meters per second, given that 1 mile is 1.609 kilometers? Okay, so this is a dimensional analysis problem. So we first start out with 549.99 miles per hour, okay, per 1 hour. And we want to convert this to meters per second. So meters per second. Okay, so in this case we need to convert our distance and our time unit. Okay, so we're going to start multiplying by our conversion factors. Now converting distance first, we know that here in 1 mile we have 1.609 kilometers. Okay, which cancels out the miles because one is on the top and one is in the bottom. Next, we know that we want it in meters, so we need to convert kilometers to meters. Okay, so we will have 1 kilometer in every 1,000 meters. Now that we have kilometers on top and on the bottom, we can cancel out that. Now we see that we have converted to meters. Next, we are going to convert hours to seconds. So in 1 hour, there are 60 minutes, and in 1 minute, there are 60 seconds. Okay, so just to make sure, we have hours on the top and on the bottom, so those cancel out, and then minutes on the bottom and minutes on the top, so minutes cancel out, leaving us with meters per second, just like we want. So that means we can now multiply straight across. The answer here is 245.81 meters per second. Here's another dimensional analysis problem. A person was walking at 45 feet per minute. How fast is the person moving in meters per hour? And we have this information in parentheses. Alright, so we have 45 feet per minute, and we want to convert this to meters per hour. So 45 feet per minute. We're going to start multiplying by the conversion factors now. To convert distance first, we have here that there are 5,280 feet in 1 mile. Okay, so now feet cancel out because one is on the top and the other is on the bottom, by saying that there is 1.609 kilometers per 1 mile. So now we have miles cancel out. So now we have kilometers, and we want to convert that to meters. So we know that there are 1,000, or 10 to the 3, meters in 1 kilometer. Okay, so kilometers cancel out. Next, we're going to convert our time. So we want minutes to hours. Okay? So we know that there are 60 minutes in 1 hour. Okay, so now minutes cancel out, and we have meters per hour. Now we can go ahead and multiply straight across. Right, and the answer here is 822.78 meters per hour. Determine whether oxygen is a nonmetal, metal, both, or neither. So if we look at the periodic table for oxygen, okay, it's represented by the chemical symbol of O. We see that it is in the right side, upper right side of the periodic table, and we know that that section is nonmetal. Here we have an isotope problem. How many protons and neutrons does C13 have? Okay, so another way of writing this is like this, or we can also add its atomic number of 6 right there, okay? And when we look at this, we know that C represents the chemical symbol that indicates carbon. 6 is the number of protons, okay, in carbon, and 13 here is going to be the mass number. Okay? And we know that mass number is protons plus neutrons. Okay, so if we know that it has 6 protons, okay, then we can put a 6 here, and we know that the mass number is 13. So what plus 6 is going to be 13? Well, the number of neutrons must be equal to 7, because 7 plus 6 is 13. So this carbon has 6 protons, like all carbon atoms do, and 7 neutrons. Right? In a neutral atom, the number of protons will equal the number of electrons. So protons is going to be equal to the number of protons is going to be equal to the number of electrons, okay, in a neutral atom, because you need to have equal amounts of positive and equal amounts of negative so that you can have a neutral atom, meaning that it has no charge. What is the average atomic weight of an element with one isotope with abundance 96.94% and mass 39.963, another occurring at 0.65% with mass 41.959, and the rest isotope with mass 42.959. Okay, so we have our percentages and we also have our masses. The masses are usually counted in AMU, okay, atomic mass units. Alright, so in order to find the atomic weight of this element, we're going to have the equation of the percent of isotope A times the mass of isotope A, and then we're going to add that to the percent of isotope B times the mass of isotope B, and just keep going, okay, until we have done that for all of our isotopes in this problem. Right, so when we write the percent of these isotopes, we're going to convert them to decimal form. So the first one is going to be 96.94%, and when converted to decimal, that is going to be 0.9694. Okay, and we're going to multiply that by the first isotope's mass, which is 39.963. Okay, so the first isotope is done. Next, we're going to do it with the second isotope. So 0.65% is going to be converted to 0.065 in decimal form, times the mass of B, which is 41.959. So that's of the second isotope. And we're going to add this to the third isotope's information. And for this one, it doesn't tell us straight out what the percentage is, but we can figure it out, assuming that the isotopes add up to 100%. 100% is going to be made out of 96.94% plus the 0.65% plus the unknown percent, so the x. Okay, and now we're going to see what x is, and x is equal to 2.41%. Converted to decimal form, we have that this percent is equal to 0.0241. Okay, and that will be times the mass of that isotope, so 42.959. Okay, and the answer is 42.50 rounded to the nearest hundredth. And this is going to be the average atomic weight of this element. If the mass number of strontium is 88, how many neutrons does it contain? Alright, so here we know that the mass number is going to be 88, and we know that we're dealing with strontium. And so strontium, if you look on the periodic table, is represented by Sr, and we know that strontium has 38 protons. Now remember, mass number is equal to the number of protons plus the number of neutrons. So if we have 38 protons, we know that we must have a certain number of neutrons, given that we know the mass number. Okay, so mass number is 88, and this equals the number of protons plus the number of neutrons. So what value must n be so that when it is added to 38, it equals 88? Well, we just subtract 38 to both sides. The number of neutrons is going to be equal to 50. So iodine, fluorine, chlorine, and nitrogen are all examples of what? One choice we have is diatomic elements, second choice is metals, third choice is halogens, compounds is the fourth choice. The answer here is number 1. Iodine, fluorine, chlorine, and nitrogen exist in nature as diatomic elements, bimolecular compounds. Which is the correct formula for cesium oxide? Alright, so cesium is represented by Cs, and oxide is telling us that we have oxygen. Now, cesium is a metal and oxygen is a nonmetal. So having a metal and a nonmetal tells us that we have an ionic compound. And for ionic compounds, we do not use prefixes used in covalent compound naming. Alright, so here we know that the ionic charge of cesium is +1, and we know that oxygen has a -2 charge. And you can tell this from the periodic table. Now, cesium oxide is a neutral compound, okay, so its total charge is 0. And so far we have a +1 and a -2 involved. And clearly this does not equal 0, so we need to add another +1, okay, so that we can have a neutral charge, which means that we have 2 cesiums. Okay, so it's going to be CS2O for the formula of cesium oxide. So see what elements you have to know if it's ionic or covalent, and then see the ionic charges and know that you want it to be a neutral charge in the end, and so then add the appropriate amount of each element to the compound so that it has a neutral charge. When magnesium and chlorine join in an ionic bond, the compound they make is called, right, so we have magnesium, which is represented by Mg, and chlorine, so Cl. And we want to join these up into a neutral compound. Now looking at the ionic charges, magnesium has a +2 charge and chlorine has a -1 charge. And we want the entire thing to be 0. So far we have a +2 involved and we have -1 involved. However, this +2 minus 1 is not 0, so we know that we need to subtract another one. Okay, so that we have 2 minus 1 minus 1, which is going to be 0, which means that we need to add another chlorine, okay, another -1. So the formula is going to be MgCl2. And when we look at this, we know that its name is magnesium chloride. Right, so it's the full name of the first element plus the name of the second element, chlorine, but with the ending IDE for the second element. What is the name of Sr3N2? Okay, so Sr is strontium, and this information can be found from the periodic table. And N means nitrogen. Okay, so we know that we have strontium and nitrogen. We know that strontium is a metal, while nitrogen is a nonmetal. So this is going to be ionic. Because it is ionic, we do not have to worry about Greek prefixes. And so we have the full name of the first element, strontium. Then we have the name of the second element with the ending IDE, so strontium nitride. Again, when you are naming an ionic compound with a main group metal, such as strontium, the name is going to be the full name of the first element plus the name of the second element, but with the ending of IDE. Find the chemical formula for iron 3 sulfide. Alright, so we have iron and we have sulfur, and we know that these two, okay, iron is going to be a metal, and sulfur is going to be a nonmetal, which means we are dealing with an ionic compound. And notice we are dealing with an ionic compound with a transition metal, okay? Iron is represented by Fe, and sulfur is represented by S. This Roman numeral here tells us that iron has a +3 charge. Looking at the periodic table, we see that sulfur has an ionic charge of -2. Iron 3 sulfide is going to have a 0 charge, a neutral charge, okay? And so far, if we put one of each together, we have a +3 minus 2, which is not 0, okay? So we need to figure out how many of each do we need to make this 0. Well, as it turns out, if we put 2 of these together, 2 irons, plus 3 sulfurs, we have from iron, right, 2 +3s, that's +6. And then if we have 3 -2s, well, that's -6. So this is going to be the compound or the chemical formula for iron 3 sulfide. Here is another naming problem. Diphosphorus pentaoxide has the formula. Okay, so we need to find the formula. So diphosphorus pentaoxide. So notice that we have di and we have penta, which means these are prefixes, okay, which means this is a covalent or molecular compound. Okay, either name works. Okay, and we know that these types of compounds are made of 2 nonmetals, or more nonmetals, okay, but in this case it's just 2. So we have diphosphorus, so phosphorus is represented by P, and we have pentaoxide, so oxide we know represents oxygen. Okay, so we have a P and an O. Okay, we have di, which means 2. Okay, so 2 of these, 2 phosphoruses, and pentaoxide, so we have penta, which means 5. So this is going to be the formula for diphosphorus pentaoxide. Find the percent composition of titanium in titanium 2 nitride. Alright, so this is why naming is important, because titanium 2 nitride, well, we need to know the formula of that. So titanium is represented by Ti, and nitride we know is referring to nitrogen. Okay. Now we know that nitrogen has an ionic charge of -3, and titanium, it tells us in this Roman numeral that it has a +2 charge. Okay, so the formula here is going to be Ti3 and 2. Okay, so again, when you name this, just figure out how many titaniums and how many nitrogens of the smallest number you need to combine, so that all in all, the compound has a 0 or neutral charge. So now that we have found our formula, we can go ahead and find the molar mass. Okay, because percent composition, okay, this is going to be equal to the mass of the element of interest. Okay, so in this case, it's going to be mass of titanium that is present here, divided by the molar mass. Okay, so the mass of titanium and nitrogen combined in their compound. And that's just going to be the sum, so the weight of the 3 titaniums plus the weight of the 2 nitrogens. So each titanium is going to be 47.87, and we're going to multiply this by 3 because there are 3 titaniums. Okay, we're going to add this to the weight of nitrogen, which is 14.01, and we're going to multiply this by 2 because there are 2 nitrogens. Okay, and you can get the atomic masses from the periodic table. The molar mass here is going to be 171.63 grams per mole. Now that we have the molar mass, we can start writing out our equation. So the percent composition, okay, is going to be equal to the mass of titanium present. So this is going to be the mass of titanium present. Okay, each titanium is 47.87 grams times 3 because there are 3 titaniums. And it's going to be divided by the molar mass, which we just found, so 171.63. Okay, and this is going to give our percent composition for titanium. This is going to give the value of 0.8367, and when converted to percent, right, we're going to convert decimal to percent, we have 83.67%. Okay, we just multiply this by 100. So it's this times 100 is going to give you a percent. What is the percent composition of carbon in C5O10? Alright, so again we have percent composition equal to the mass of that element present. Okay, so we have carbon divided by the molar mass of this compound, and it's going to be times 100 to convert it to a percent. So the mass of carbon present is going to be the 12.01, right, is each carbon, but we have to multiply it by 5 because there are 5 carbons. Next, we're going to divide it by the total weight, which is the weight of 5 carbons plus the weight of the 10 oxygens. So each oxygen weighs 16 grams per mole, and we're going to multiply this by 10 because there are 10 oxygens. We get the value of 0.2729, and if we multiply this right by the 100 to convert it to a percent, we get 27.29%. Okay, so just remember, if you don't multiply it by 100 beforehand, you'll come out with a decimal, and you can convert that decimal to the percent by multiplying by 100. Find how many molecules of water there are in 12.5 grams of it. Alright, so we know that we need to go from grams to moles to molecules. Okay, and we're talking about water, which has the formula of H2O. Right now we start with grams, okay, and so we need to convert to moles. To convert to moles, the number of moles here is going to be equal to the given mass divided by the molar mass. Or we could also say it's going to be the given mass times the conversion factor. So the molar mass of water is going to be the weight of 2 hydrogens plus the weight of an oxygen. So we have 18.02 grams per mole. Okay, and so the given mass is going to be 12.5 grams, and we're going to divide that by 18.02 grams per mole. This gives 0.69 moles. Another way you could write this is that 12.5 grams times a conversion factor of something that puts grams at the bottom is at 18.02 grams and 1 mole at the top. So you have grams at the top and grams at the bottom. So these cancel out and you're left with moles. Still, as you see when you do this math, right, it's just the same as this. Okay, so this is going to be in moles. And then we're going to convert moles to molecules. So molecules, this number is going to be the number of moles, so 0.69 moles, times Avogadro's number, 6.022 times 10 to the 23rd. And this is going to give us 3.79 times 10 to the 23 molecules. When there are 14.79 grams of sodium chloride, how many moles of the salt is this? So as usual, we need to identify the compound here, sodium chloride, which is NaCl. Okay, and we know that to find moles, we need to have the given mass over the molar mass. This is why naming is important. To find the molar mass, we need to know the chemical formula of sodium chloride, okay, which is this. So we have the given mass, which is 14.79 grams, and this is going to be divided by the molar mass, which is the weight of sodium, plus the weight of chlorine. So we have 23 plus 35.45, okay, in grams per mole. And this is going to give 0.25 moles. Okay, another way of doing this is saying 14.79 grams, okay, times the conversion factor of the molar mass, 164.8 grams per 1 mole. And as you see, grams on top, grams on the bottom, we can cancel out grams, leaving us with moles. And this would just be multiplied straight across, but it's the same thing as this. Thank you so much for watching this video. I really hope you found it helpful. If you did, remember to subscribe and leave a comment down below. I'll see you next time.